Hello and welcome to another Clear Sky Explainer video. In this video, we'll take you through an aircraft's climb phase where power meets altitude. First, we will discuss the best angle of climb, known as VX. Achieving an optimal climb out is essential for safe and efficient flight operations. The best angle of climb, VX, refers to the speed at which an aircraft gains the most altitude over the shortest horizontal distance after takeoff. Pilots use VX when it is necessary to clear obstacles at the end of the runway or during other critical phases of flight. Maximizing altitude gain over a given distance is crucial in situations with limited climb space. For example, VX is particularly important when departing from short runways or airports surrounded by high terrain. How does this relate to the climb gradient? Let's have a look. For a steady climb, thrust must overcome both drag and a component of weight, which is weight times the sine of the aircraft's flight path angle. Then we can rearrange to isolate sine of the flight path angle. For shallow climb angles, which is typical in aviation, sine of the flight path angle is approximately the tangent of the flight path angle. Why? Because for small angles, less than 15 degrees, sine of the angle and tangent of the angle are nearly equal. And tangent is the gradient of sine and cosine. By definition, gradient is the ratio of vertical rise to horizontal distance. So we can assume that tangent is equal to the climb gradient. We now arrive at the final formula. The climb gradient equals thrust minus drag divided by weight. This formula highlights the relationship between the forces acting on the aircraft during climb. More simply put, more excess thrust equals a steeper climb. Vx is the speed where thrust minus drag is maximized to achieve the biggest possible gradient. This also implies that various factors, such as aircraft weight, atmospheric conditions, and engine performance can influence the actual climb gradient achieved. For jets, Vx will be close to the speed for minimum drag, and for props it will be close to 1.1 times the stall speed. Let's have a closer look at these factors. The primary factors affecting climb gradient are altitude, temperature, weight, and bank angle. As altitude increases, air density decreases. Lower air density means less oxygen for the engines, resulting in reduced thrust. Higher temperatures reduce air density, which decreases both engine performance, lower thrust, and wing lift, resulting in a reduced climb gradient. Taking off in hot conditions at high-altitude airports significantly impacts climb capability. The next factor is weight. The relationship between weight and climb performance is straightforward. Heavier aircraft require more lift and thrust to climb, which reduces the climb gradient. Managing aircraft weight is essential for optimal climb performance. Every additional pound carried affects the aircraft's ability to gain altitude efficiently. The final factor is bank angle. Banking the aircraft increases drag and reduces the vertical component of lift. This makes it more difficult for the aircraft to maintain or increase altitude during a climb. As a result, climb gradient is reduced and the aircraft's ascent becomes less efficient. Wind is a critical factor in aircraft climb performance. A headwind during takeoff improves climb performance by increasing the aircraft's climb gradient. This is because a headwind reduces ground speed while airspeed remains the same. This allows the aircraft to gain altitude more efficiently after liftoff. A tailwind, in contrast, decreases climb performance by reducing the climb gradient. This makes it more difficult for the aircraft to reach the desired altitude efficiently. Flaps are often associated with increased lift, leading to the assumption that they are beneficial for climb performance. However, while flaps do increase lift, they also significantly increase drag. The additional drag from flaps means that climb gradient is not improved when flaps are extended. For optimal climb performance, flaps should be retracted, resulting in a clean wing configuration. This does not contradict the use of flaps during takeoff. Flaps are essential for reducing takeoff distance and achieving the required climb performance, including reaching the takeoff safety speed, V2. They enable the aircraft to lift off at a lower speed, which is critical for operations on shorter runways. So, a higher flap settings shorten the takeoff run but worsen the climb gradient, while lower flap settings lengthen the takeoff run but improves the climb gradient. Previously, we discussed the best angle of climb, or Vx. Now let's focus on the best rate of climb, Vy. Vx is used to maximize altitude gained over a given distance. Vy, on the other hand, is used to maximize altitude gained over a given period of time. This means you reach a higher altitude in the shortest possible time. Vy is typically used after clearing obstacles and when a rapid climb is required. The rate of climb is calculated by multiplying the true airspeed with sine of the flight path angle. Since we already know what sine of the flight path angle is equal to, we arrive at the final formula. Rate of climb equals the true airspeed multiplied by thrust minus drag divided by the aircraft's weight. This calculation shows how efficiently the aircraft converts forward speed into altitude during a climb. And Vy is the airspeed where the best rate of climb is achieved. This brings us on to the last subject. The rate of climb is directly related to the power available to the aircraft. Power available is true airspeed multiplied by thrust, while power required is true airspeed multiplied by drag. Thus, power represents the rate at which work is done to sustain flight. If we take the formula for rate of climb, we can now reduce this to show that the rate of climb is equal to excess power available. We notice that greater available power results in a higher rate of climb. The type of engine, jet or piston, significantly affects climb performance. Jet engines are designed to maintain strong performance at higher altitudes, providing consistent power output during climb. This allows jets to climb efficiently and sustain power as altitude increases. Piston engines, in contrast, are optimized for lower altitudes. As a piston engine aircraft climbs, its power output decreases with altitude, reducing climb performance. This graph shows that piston aircraft have limited excess power at high speeds, making the climb performance better at moderate speeds. Jets generate more power as speed increases, allowing better high-speed performance and thus requiring a higher speed for the best climb. If you found this information valuable, please consider giving this video a like and subscribe for more aviation insights. Thank you for watching. Until next time, clear skies and happy landings.